So one thing that's going to be useful to us as we think about our hardware choices is to say, well, how do we, as we make n bigger and bigger and bigger, what can we say about the cost that we're incurring? If I double the size of the operands, how does the size or latency or throughput of my circuit change as n changes? And what we've done in computer science, because it's sort of an abstract notion of the complexity of a circuit, what we do is we've invented this order of notation, and you can see there's this capital theta here. And order of is giving us a sense of how it grows, sort of ignoring the little details, the little constants. And so if I can say something grows linearly or something grows quadratically, those two have quite different hardware costs as I double the size. Okay, and I'm not particularly I don't need to tell you a whole lot about the exact equation to compute the hardware costs from the size of the operands. I'm just trying to give you a feel for how those costs grow as the operands get bigger and bigger and bigger. Sort of a qualitative sense of what happens. And so the order of here's an example right here. Here's a detailed formula, and we say, well, how does that formula grow as n gets bigger? And as I add a little bit to n, and then I say n goes from 1 to 2 to 4 to 8 to 16 to 1 million to 2 million to 4 million, give me a sense of how it's growing. What I would say is that after a while, as n gets very big, there's one term in this equation that dominates. Right? It's the one that really determines the value. So if you think about, a billion squared plus 2 times a billion plus 3, well, the plus 3 hardly makes any dent in the answer at all. And even the 2 billion there, it doesn't matter, because a billion times a billion is most of the answer. Right? So we say that the order of growth of the size of the result of if this was an equation for the size, the order of growth for the size would be order n squared. Right? And there's a little mathematical thing here that shows what we mean. It's bounded both above and below by n squared. So for particular constants C1 and C2, the value of this equation is always greater than C1 times n squared and less than C2 times n squared for almost all n. It's not true for very small n, but for finitely number of n, we might violate that inequality. But there's a lot of possible n's, a lot of integers. And for almost all of them, all but finite number of them, we can pick C1 and C2 so that inequality is true. So that'll give us a way of a little shorthand. It's like a little EPA sticker on the window of our circuit that gives us a quick glimpse as to the space required or the amount of hardware required or the latency or the throughput. So what we're going to do is start thinking about the hardware costs and the latency and the throughput of these circuits. And we're going to actually use our pipelining skills from the previous lecture to build a whole variety of multipliers that achieve different design goals. Okay, so we can count up the number of things. We have n squared partial products. The widest adder width, if you looked across here, is 2 times n. And so forth and so on. And so the total hardware cost is the sum of all this, and we can come up with sort of a complicated formula here if we want. But in general, what we want to do is to say, look, if I have an equation that involves an n squared term and some n terms and some constants, that the hardware cost is on the order of n squared. In other words, as I would double the size of my operands, I would expect, sort of naively, if these are indeed the hardware costs associated with our hardware picture, I would expect to quadruple the amount of hardware that I need. Right? Because 2 squared is 4. Everybody sort of happy with that? So this is just a way, a quick sort of, give you a quick overview of how many, in this case, pieces of hardware we need to build a multiplier. And you might say, well, look, if I have the AND gates are forming the partial products 1 bit at a time, and I have n squared of those, and then I have all these full adders. I need a lot of each individual building block here of adding together bits in a column. I'll ultimately need about n squared of those adders. So it would seem like if I had to put the data through all of that, maybe the time it takes for my multiplication circuit to run is n squared. And if you think about how you did it, you can see how as you were thinking about the number of things you wrote down here, you wrote down about n squared things given the n-bit operands. Right, so that gives you a sense of how long it might take to actually do the problem. Now at this point you might say, well, gosh, this is lots of machinery we're inventing here. We must be getting someplace interesting, although this all seems to be a rehash of second grade right at the moment. And you could say, isn't this sort of a, how can I do better than that? Could I get a multiplier that has less hardware cost or higher throughput or better latency? So that's really what the problem we're trying to set up is that problem. Yes, sir?
Does this multiplier actually have n squared latencies? I feel like the longest path through it is like a quarter of that.
I think if we look at the next couple slides, you'll be proven exactly correct. So the naive analysis, sometimes we have to be a little careful, and in fact we're going to spend a slide or two being careful and come up with a different number. But good insight, and we're getting there slowly.